Hi students, welcome to my virtual classroom. Here you will learn chemistry for higher secondary classes. The classroom offers a series of video classes on each chapter. We started with the basic concepts of chemistry, the first unit of class 11 chemistry. Since animations speak louder than words, I have included a lot of animations in these video classes. But remember, animations never represent the real situations. However, it will help you to understand the concepts more clearly and to boost your learning retention. I am Dr. Sirek Matthew, a retired professor in chemistry. The purpose of my channel Chemistry Master is to upload video classes related to NEET, JEE Main and Advanced, KEAM, CUET and other competitive examinations. This is part 3 of the video series on the chapter Basic Concepts of Chemistry. Here you will learn about the laws of chemical combination, atomic and molecular masses, mole concept, etc. Towards the end of the video, multiple choice and numerical type questions are discussed. You need not view the whole video at a single stretch. You can use video chapters given in the description bar to view different sections of the video. The last part of this video series will be uploaded soon. These videos are meant for classroom learning. A concise form of these videos with more multiple choice questions, including previous year questions and their explanations, will follow, enabling you to prepare for competitive examinations. If you like the video, please subscribe my channel and forward to others. Don't forget to hit the like button. Let us start. There are 5 laws of chemical combination. The word combustion or burning is quite familiar to you. You know that it requires the presence of oxygen. But for the earlier scientists, it was a difficult puzzle. They couldn't explain how it occurs, even though combustion was used as early as 1300 CE for extracting iron from iron ore. In 1774, Antoine Lavoisier performed an experiment. He took some tin pieces in a stout glass tube and fused the end of the tube, enclosing some air in it. Then he weighed the glass tube with its contents and found the total mass. Then he strongly heated the tube. The tin pieces turned into a dull white powder. At that time, it was called tin calx, meaning calcined tin. We now know that it is nothing but tin oxide. He again weighed the glass tube and its contents, glass vessel, tin calx, and the remaining air. To his astonishment, he found that the total mass before and after heating remained the same. This led him to propose the first law, that is, the law of conservation of mass. Through further experiments, Lavoisier showed that the product of reaction tin calx, that is tin oxide, consisted of the original tin together with a portion of air. He was convinced from similar experiments that oxygen from air is essential to combustion and also led him to formulate the law of conservation of mass. The law could be stated as, during chemical reaction, the total mass of products formed will be same as the total mass of the reactants taken, or matter can neither be created nor be destroyed. We can illustrate the law using the following simple experiment. I have taken selenium solution in the beaker and potassium chloride solution in the measuring jar. Now I am taking the total mass, including the tray, beaker and a measuring jar, and it is equal to 175.625 gram. Now what I am going to do is, I am mixing the solutions. I am pouring potassium chloride solution into the selenium solution. A reaction has occurred. Silver nitrate reacted with potassium chloride giving silver chloride and potassium nitrate, and the silver chloride appears as the white precipitate. Now again I am taking the total mass, and the total mass is exactly same as that taken earlier, 175.625 gram. That is, mass is conserved during chemical reaction. The law of definite proportions or the law of definite composition. In 1799, Joseph Proust, a French chemist, reported the conclusion that he arrived at from his experiments. In his own words, 100 pounds of copper dissolved in sulfuric or nitric acids and precipitated by the carbonates of soda or potash invariably gives 180 pounds of green carbonate. The green carbonate is copper carbonate. He used different methods for preparing copper carbonate, but the amount of copper carbonate obtained was the same. This and similar observations became the basis of the law of definite composition or the law of definite proportion. The law can be stated as a given compound always contains exactly the same proportion of elements by weight. Let us consider two samples of copper carbonate, one natural and the other one synthetically prepared. The natural sample of copper carbonate, or more correctly basic copper carbonate, and it is obtained as a green patina, that means a green film on the surface from the surface of ancient copper or bronze statues. And the second one is synthetically prepared in the laboratory. Analysis gave the following data: natural sample, synthetic sample, the percentage of copper, percentage of carbon, and percentage of oxygen. In the natural sample, the percentage of copper is found to be 51.35, that of carbon now 9.74, and a percentage of oxygen 38.91. The synthetic sample, percentage of copper, same as the above, that is 51.35, 9.74, 38.91. That is, whether it is natural sample or synthetic sample, the percentage of the different elements present are the same. Another example is water. So water sample collected from well or a river. The percentage of oxygen and hydrogen will be the same. 88.91% oxygen and 11.19% of hydrogen. All samples of a compound have the same composition, the same proportion by mass of the constituent elements. John Dalton, an English school teacher, used the two fundamental laws of chemical combination we just have studied, that is the law of conservation of mass and law of definite proportions, to develop his atomic theory. The assumptions made in his theory led to the prediction of the law of multiple proportions. We will study more about Dalton's theory later in this video. The law could be stated as: if two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. As an example, we can take hydrogen and oxygen. Hydrogen and oxygen react together giving water. Hydrogen and oxygen also react together giving hydrogen peroxide. In the formation of water, 16 gram of oxygen combined with 2 gram of hydrogen giving 18 gram of water. In the formation of hydrogen peroxide, 32 gram of oxygen combined with 2 gram of hydrogen giving 34 gram of hydrogen peroxide. Here the mass of hydrogen is fixed, that is 2 gram. Now the different masses of oxygen that combine with the fixed mass of hydrogen are 16 and 32. Now from the law, there should be a simple ratio between these two masses, that is 16:32 or 1:2. And this ratio is a simple ratio as suggested by the law. Another example is carbon and oxygen. Carbon and oxygen react to give carbon dioxide and also carbon monoxide. In the formation of carbon dioxide, 32 grams of oxygen react with 12 grams of carbon, giving 44 grams of carbon dioxide. In the formation of carbon monoxide, 16 grams of oxygen react with 12 grams carbon, giving 28 grams carbon monoxide. So the mass of carbon is fixed. Now the different masses of oxygen are 32 and 16. Therefore, these two masses, there must be a simple ratio, that is 32:16 or 2:1. The fourth law is Gay-Lussac's law of gaseous volumes. In 1808, Gay-Lussac reported that gases react by volumes in the ratio of small whole numbers, provided all gases are at the same temperature and pressure. Thus, 100 ml of hydrogen combined with 50 ml oxygen to give 100 ml water vapor. All are at the same temperature and pressure. Now, volume of hydrogen is to volume of oxygen is 2:1, 100:50 or 2:1. Similarly, the volume of hydrogen is to oxygen is to water vapor. That also is 2:1:2. And these two ratios are simple ratios. Another example is 1 volume of hydrogen reacts with 1 volume of chlorine, giving 2 volumes of hydrogen chloride gas. Now the ratio of the reactants, that is all our gases, is 1:1:2. The law could be stated as, at constant temperature and pressure, the volumes of gases that react or are formed can be expressed as a ratio of simple whole numbers. Remember, Gay-Lussac's law does not apply to any solid or liquid reactants or products that might be present. Gay-Lussac's discovery was actually the law of definite proportions by volume. The law of definite proportions, which we studied earlier, was with respect to mass. However, Dalton did not agree with this proposition. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. The fifth law is Avogadro's law. In 1808, Gay-Lussac proposed that gases react by volumes in the ratio of small whole numbers, but he couldn't give a reasonable explanation for his observation. In 1811, Amedeo Avogadro explained this by suggesting his equal volumes, equal number hypothesis. A hypothesis means a guess or proposed explanation which is to be proved later. Avogadro made a distinction between atoms and molecules, which is quite understandable to us. But at that time, his hypothesis and its implications were not understood by his contemporaries, including John Dalton. He did not accept the concept of molecules. Avogadro's hypothesis could be stated in either of the two ways. Equal volumes of all gases at the same temperature and pressure should contain equal number of molecules, or equal number of molecules of different gases at the same temperature and pressure occupy equal volumes. For example, 2 volumes of hydrogen react with 1 volume of oxygen, giving 2 volumes of water vapor. For simplicity, 2 volumes of hydrogen contains 10 molecules of hydrogen. Then 1 volume of oxygen should contain only 5 molecules of oxygen, and 2 volumes of water vapor should contain 10 molecules of water. That is from the Avogadro's law. And in this case, all are at constant temperature and pressure. Avogadro suggested that molecules of gas may break up into half molecules when they react. Now we know that oxygen molecules split into atoms which then combine with molecules of hydrogen to form water molecules. In this way, volume of oxygen needed is only one half of that of hydrogen. In fact, Avogadro was a scientist ahead of his time. His hypothesis was effectively communicated by Stanislao Cannizzaro about 50 years later. Let us consider the Dalton's theory in some more details. The Greek philosopher Democritus, between 460 and 370 BC, BC means before Common Era, Democritus suggested that all matter is composed of tiny, discrete, indivisible particles that he called atoms. The word atom is derived from the Greek word atomio, means uncuttable or indivisible. His ideas were based entirely on philosophical speculations rather than experimental evidences. These ideas were rejected for about 2000 years. In 1808, John Dalton, an English school teacher, tried to explain why matter behaves in such a systematic way as revealed by the first three fundamental laws of chemical combinations that we have studied earlier. The third one was suggested by John Dalton, that is the law of multiple proportion. In line with the suggestions made by Democritus, he proposed his atomic theory, and it is based on experimental observations. His theory involved the following assumptions. Each chemical element is composed of minute, indivisible particles called atoms. Atoms can neither be created nor be destroyed during a chemical change. All atoms of a given element have identical properties, including identical mass. At that time, the word used is weight. Atoms of different elements differ in mass. Compounds are formed when atoms of different elements combine in fixed ratio. For example, one atom of A to one atom of B give AB, or one atom of A to two atoms of B give AB2. Chemical reactions involve reorganization of atoms. From assumption 1, that is, if atoms of an element are indestructible, the same atoms must be present before and after reaction. Hence, the total mass remains unchanged. Thus, Dalton's theory explains the law of conservation of mass. If all atoms of an element are alike in mass, that is assumption 2, and if atoms unite in fixed numerical ratios, that is assumption 3, present composition of a compound must have a unique value regardless of the origin of the sample analyzed. Thus, Dalton's theory explains the law of constant proportions. These observations made him to predict the law of multiple proportions. We now reject his first assumption. We know that atoms can be further divided. His ideas were based on the limited experimental observations of his day. Even with their shortcomings, Dalton's ideas provided a framework that could be modified and expanded by later scientists. Thus, John Dalton is often considered to be the father of modern atomic theory. Even though Dalton's theory could explain the laws of chemical combination, it could not explain the law of gaseous volumes. He did not consider molecules. Also, his theory could not explain why atoms combine. Scientists of 18th and 19th centuries did not have sophisticated experimental facilities as we now have. Their experimental procedures were tedious and time-consuming. This picture shows a 19th century chemistry laboratory. Of course, an AI-generated image. Chemists of that time painstakingly sought information about the composition of compounds and they tried to systematize their knowledge. They understood that each element has a characteristic mass relative to every other element. Since atoms are extremely small, their masses will be very, very small. For example, mass of a gold atom is approximately 3.27 into 10 raised to minus 22 gram. Although these early scientists did not have the experimental means to measure the mass of each kind of atom, they succeeded in defining a relative scale of atomic masses. At that time, atomic weights. The term atomic weight is widely accepted because of its traditional use. But atomic mass is technically more accurate. In chemistry, we often compare amounts of substances under the same gravitation. So any weight ratio is same as the mass ratio. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1, that is without unit, and other elements were assigned masses relative to that. Hydrogen, atomic mass 1. Now let us see mass of a carbon atom relative to hydrogen atom. Let me use a balance. Now I am placing a single carbon atom in this pan. Now I compensate the weight by placing hydrogen atoms. I placed 4 hydrogen atoms, not balanced. 4 more, total 8, again not balanced. Now 4 more, total 12, it is balanced. Now we say that the mass of carbon atom is 12 relative to hydrogen. Later, hydrogen was discarded as a standard for relative atomic mass as it could not give consistent values for heavier elements. This is because hydrogen has the lightest atom. So any measurement error in its mass will cause large error in the calculation of relative mass of heavy atoms. Moreover, hydrogen gas is reactive and difficult to obtain pure, isotopically consistent form. Ordinary hydrogen, protasium, is abundant but always contains traces of deuterium. Then oxygen was selected and assigned a value of 16. Physicists defined the AMU as 1 by 16 the mass of oxygen 16 atom, while chemists defined it as 1 by 16 of the average mass of oxygen atoms found in nature, which are a mixture of oxygen 16, oxygen 17, and oxygen 18. Because chemists included heavier isotopes, their atomic mass unit was slightly larger than the physicists' unit. This was confusing and created inconsistencies. But neither of these standards could provide values of atomic mass of elements without discrepancies. In 1961, carbon-12 is adopted as standard for calculating atomic masses of elements by the International Union of Pure and Applied Chemistry, abbreviated as IUPAC. Carbon-12 was chosen because it is isotopically pure, stable, easy to handle, mid-mass, that is reducing relative error, and resolved historical inconsistencies between physics and chemistry atomic mass scales. Mid-mass means lighter than most metals, heavier than hydrogen. That minimizes rounding errors in relative mass comparisons. At present, we can measure experimentally the accurate mass of atoms using mass spectrometers. The picture shows a present-day lab with high-end instruments. This is the mass spectrometer and its accessories. The mass spectrometer is a device by which we can measure the accurate mass of atoms. Most elements have atoms of different masses. Such atoms are called isotopes of the elements. Natural abundance of these isotopes vary. For example, carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. Carbon-12 has the highest natural abundance. that is 98.892%. Carbon 13 only 1.108%. And carbon 14 2 into 10 raised to minus 10%, that is practically nil or trace amount. So we have three isotopes, carbon 12, carbon 13 and carbon 14. The isotopes of hydrogen are prosium, atomic mass 1, and the percentage abundance is 99.988%. Then deuterium, atomic mass 2, its abundance is 0.012%. Tritium, that is radioactive, and it is present only in trace amount. Its atomic mass is 3. Carbon 14 also is radioactive. Isotopes of oxygen are, the major isotope is oxygen 16, that is 99.757%. Oxygen 17, 0.038%. Oxygen 18, 0.205%. As said earlier, in 1961, both the chemists and the physicists adopted carbon 12 isotope as the standard and assigned a mass exactly equal to 12 atomic mass unit, AMU. One atomic mass unit is defined as a mass exactly equal to 1/12 mass of a carbon 12 atom. Just imagine that I am cutting a carbon atom using a knife into exactly 12 equal pieces. And now I am taking one out of that, and this part is 1/12 of the carbon atom, and this is taken as 1 AMU. 1 AMU is equal to 1.66056 into 10 raised to minus 24 gram. At present, atomic mass unit, that is AMU, is replaced by unified mass with the symbol U. If you consider relative atomic masses, an oxygen atom should be 16 times heavier than 1/12 of a carbon 12 atom. If you look at the table of atomic masses, none of the elements have whole number atomic masses. The masses of atoms relative to carbon 12 are determined using mass spectrometer. In a table of atomic masses, the value listed for oxygen is 15.994 AMU or U. In fact, the actual masses of individual atoms in atomic mass units are never whole numbers except for carbon 12. Why the difference? The atomic mass unit is defined based on a sample of carbon assumed to be containing only carbon 12 atom, and a value 12 AMU is assigned to it. The mass spectrometer calculates masses based on that. But in an actual experiment, we cannot take a sample containing oxygen 16 alone. It involves other isotopes of oxygen such as oxygen 17, oxygen 18 with varying natural abundances. So we get weighted average for molecular mass, which will not be a whole number. Therefore, the atomic mass of an element is the average of the isotopic masses, weighted according to the naturally occurring abundances of the isotopes of the element. In a weighted average, we must assign greater importance, that is, give greater weight to the quantity that occurs more frequently. In the case of oxygen, the more frequently occurring isotope is oxygen 16 with a natural abundance of 99.757%. Let us see how to calculate the average atomic masses. The table shows isotopes of oxygen, carbon and hydrogen, corresponding percentage abundances and the atomic masses obtained from mass spectrometer. Oxygen has three isotopes, oxygen 16, oxygen 17 and oxygen 18. The percentage abundance of oxygen 16 is 99.757 and the mass obtained for oxygen 16 from mass spectrometer is this one. Oxygen 17, the percentage abundance is very low, 0.038, and for oxygen 18 it is 0.205. We can use a general equation for calculating the average atomic mass of an element. Atomic mass of an element is equal to fractional abundance of isotope 1 into mass of isotope 1 plus fractional abundance of isotope 2 into mass of isotope 2 plus etc. Fractional abundance means the percentage abundance divided by 100. For oxygen 16, the percentage abundance is 99.757 and we divide it by 100, we get 0.99757. So, the atomic mass of oxygen could be calculated as follows. 0.99757, that is the fractional abundance of oxygen 16 into mass 15.994915 U plus 0.0038 into 16.99132 plus 0.00205 into 17.999160 U equal to 15.99405. When corrected to the required significant figures, it is 15.99941. Similarly, we can calculate the average atomic mass of carbon as 12.0107. Only for carbon 12, the atomic mass is a whole number. For hydrogen, it will be 1.00794 and oxygen it is 15.9941. Atomic and molecular masses. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. Thus, molecular mass is the weighted average mass of one molecule expressed in atomic mass unit U. For example, take water. Water contains 2 hydrogen atoms and 1 oxygen atom. Molecular mass of water equals 2 into atomic mass of hydrogen plus 1 into atomic mass of oxygen equals 2 into 1.00794 U, that is average atomic mass of hydrogen, plus 15.9994 U, that of oxygen, equals 18.0153 U. Next is formula mass. Formula mass is the mass of a formula unit in atomic mass units. It is mainly used in the case of ionic compounds. Ionic compounds do not contain discrete molecules as their constituent elements. In such compounds, positive and negative ions are arranged in a three-dimensional structure. An example is sodium chloride. So this is one formula unit, one chloride ion and a sodium ion. Formula mass of sodium chloride equals atomic mass of sodium plus atomic mass of chlorine, that equals 22.9898 atomic mass of sodium plus 35.453 atomic mass of chlorine, that is 58.4428 or 58.443 U. Formula mass of magnesium nitrate will be atomic mass of magnesium plus, there are 2 times NO3, so 2 into atomic mass of nitrogen plus 3 into atomic mass of oxygen, that is 24.30550 plus 2 into 14.0067 plus 3 into 15.9994. So the formula mass of magnesium nitrate is 140.3148 U. The term formula mass and molecular mass have essentially the same meaning, but when referring to ionic compounds, formula mass is the proper term. Mole concept and molar masses. Atoms and molecules are extremely small in size and are not visible to our naked eyes. But their numbers in even a small quantity of any substance is really very large. For example, 0.1 gram of gold contains approximately 3.06 into 10 raised to 20 gold atoms. To handle such large numbers, we need a unit of convenient magnitude. The unit we use in the case of microscopic, that means extremely small entities, is the mole. The symbol is MOL. Just as we denote 1 dozen for 12 items. Mole is the SI unit of amount of substance. The word entities is used to represent atoms, molecules, electrons, protons, ions, etc. According to 2019 revision of SI units, 1 mole is defined as to contain exactly 6.02214,076 into 10 raised to 23 elementary entities. This number is the numerical value of the physical quantity Avogadro constant, symbol Na, expressed in per mole. Avogadro number is simply the exact numerical value 6.02214,076 into 10 raised to 23 written without units. Avogadro constant Na equals 6.02214,076 into 10 raised to 23 per mole. Avogadro number, the same symbol Na, 6.02214,076 into 10 raised to 23, written without unit. As discussed previously, 1 mole is a quantity containing as many as this much entities. This number is enormously large and beyond our imagination. It is very difficult to get an idea of the vastness of this number. This is because such numbers we do not encounter in our life. We usually consider lakhs and crores or millions and billions. The following example will help you to get an approximate idea of the vastness of this number. If you look at the clear starry night sky, you may be able to see about 2000 to 3000 stars with your naked eyes. But can you imagine the number of stars that may be present in the whole universe? It will be near Avogadro number. You know that a computer can perform billions of counting operations in 1 second depending on the CPU. Imagine that a computer can count up to 1 billion in 1 second. 1, 2, 3, etc. 9 nines, then 1 billion, that is 10 raised to 9. Now let us calculate the number up to which the computer can count in 1 year. In 1 minute, 10 raised to 9 into 60. In 1 hour, into 60. In 1 day, into 24. In 1 year, into 365. That is approximately up to 3 into 10 raised to 16. Now we can calculate the number of years required to count 6 into 10 raised to 23, that is 6 into 10 raised to 23 divided by 3 into 10 raised to 16, that is 2 into 10 raised to 7, that is 20 million years. Human history is nowhere near it. By definition, Avogadro number Na is, that is 1 mole is this number exactly. This is an exact number by definition and no amount of uncertainty is associated with it. This definition came effective in May 2019. In 2019, 4 of the 7 SI base units specified in the International System of Quantities were redefined in terms of natural physical constants rather than human artifacts such as the standard kilogram. The international prototype of kilogram was a cylindrical artifact. Artifact means an object made of platinum iridium alloy kept in Paris, which defined the kilogram from 1889 until May 20, 2019. Now it is redefined based on the fundamental constant of nature, the Planck's constant. The reason is international prototype of kilogram was found to be unstable and found to vary slightly with its copies over these years. Similarly, mole is defined in terms of Avogadro number. It is one among the 7 defining constant. By definition, Avogadro constant is 6.022 into 10 raised to 23 per mole, that is entities per mole. Even though this number has 9 significant figures, it is defined exactly and no amount of uncertainty is associated with it. It is one among the 7 defining constants, the numerical values of which have no uncertainty. By definition, molar mass is the mass of 1 mole of a substance in gram. The molar mass in grams is numerically equal to atomic, molecular or formula mass in U, that is unified mass. Mole is the amount of substance of a system that contain 6.022140076 into 10 raised to 23 specified elementary entities. A simple analogy will make the concept clearer. We know 1 dozen is equal to 12 things, whatever it may be, but their masses varies. For example, this bowl contains 1 dozen steel balls, say steel balls used in bearings. This bowl contains 1 dozen plastic balls like table tennis balls. Now I find the weight of these balls separately after tearing the weight of the bowl. So in this case it is 58.224. Now the plastic balls, that is 29.424 gram. Similarly, if we weigh 1 dozen cricket balls, it will be 1.871 kilogram. The mass of one steel ball will be 58.224 by 12, that is 4.852 gram. Mass of one rubber ball or plastic ball will be 29.424 by 12, 2.452 gram. Mass of one cricket ball, that is 1871 gram divided by 12, and that is 155.9 gram. We are tabulating the data. Item amount of mass: steel balls, rubber balls, cricket balls. 1 dozen, their masses. 1 dozen means 12 in numbers. All are 12 in numbers, but their masses vary. Similarly, consider this table, that is 1 mole of carbon 12 isotope. Type of it is carbon 12 atoms. 1 mole of water, the type of entities is H2O molecules. 1 mole magnesium chloride, the type of entities is magnesium chloride formula units. So here it is atomic, molecular or formula mass 12.000 U. This one, the corresponding molar mass, number of entities. Atomic mass in atomic mass unit U. Then corresponding molar mass, that is gram per mole. For carbon 12 it is 12 gram per mole. Water it is 18.0153 gram per mole. For magnesium chloride the formula mass is 95.211 gram per mole. Now the corresponding number of the items, all are the same. Avogadro number. Keep in mind, molecular mass and molar mass sound similar and related, but they are not the same. Molecular mass is the weighted average mass of one molecule expressed in atomic mass unit U. Molar mass is the mass of Avogadro number of molecules or atoms or formula units, etc., expressed in gram per mole. 1 mole equals molar mass in grams equals 6.022140076 into 10 raised 23 in number. The defined exact value of Avogadro constant is inconvenient to use in ordinary calculation. When we round off the constant, we are imposing some amount of inexactness in the quantity. We can round off Avogadro constant to 3 or 4 significant figures. So if you write Avogadro constant as 6.022 in 10 raised to 23 per mole, it has 4 significant figures. Or if it is written as 6.02 into 10 raised to 23 per mole, 3 significant figures. Now 6.022 into 10 raised to 23, that is Avogadro number, and it is a counting number, so it will have infinite number of significant figures. Let us calculate the number of water molecules that may be present in a drop of water weighing 0.05 gram. We know 1 mole H2O equals 6 into 10 raised to 23 H2O molecules, and 1 mole H2O equals 18 gram H2O. So for convenience we use approximate values, that is 6 and 18. Now first you have to find out the conversion factors. That is 1 mole H2O is equal to 6 into 10 raised to 23 H2O molecules. That is 1 mole H2O by 1 mole H2O. Then 6.6 into 10 raised to 23 H2O molecules by 1 mole H2O is equal to 1. These two cancels. Similarly, 1 mole H2O equals 18 gram H2O. So 1 mole H2O by 18 gram H2O, this cancels, equal to 1. The mass is 0.05 gram. So first we convert the mass into number of moles, that is multiplying by this conversion factor. Then we get the number of molecules by multiplying by this conversion factor. That is, final value will be 1.67 into 10 raised to 21 equals 1.7 into 10 raised to 21 H2O molecules. That is writing in the required number of significant figures. See how small is the water molecule. That is, a drop weighing 0.5 gram contains 1.7 into 10 raised to 21 H2O molecules. Now calculate the molecular mass and molar mass of glucose C6H12O6. Given atomic mass of carbon 12.011 U, atomic mass of hydrogen 1.008 U, atomic mass of oxygen 16.00 U. Now molecular mass of glucose is 6 into atomic mass of carbon plus 12 into atomic mass of hydrogen plus 6 into atomic mass of oxygen, that is 72.066 U plus 12.096 U plus 96.00 U, that is 180.162 U. Therefore molar mass of glucose is 180.162 gram per mole. Calculate the average mass of an iron atom in grams. Atomic mass of iron is 55.85 U. Atomic mass 55.85 U. Therefore molar mass of iron is 55.85 gram per mole. We know 1 mole of Fe atoms is equal to 6.022 in 10 raised to 23 atoms, and 1 mole Fe is equal to 55.85 gram. Hence the conversion factors are 55.85 gram by 1 mole Fe atoms equal to 1. 1 mole Fe atoms by 6.022 in 10 raised to 23 atoms equal to 1. So mass of an iron atom is conversion factor into this one, and that is 9.274 into 10 raised to minus 23 gram per atom. That is the mass of one iron atom. Now calculate the number of carbon dioxide molecules present in 31.6 gram carbon dioxide. Atomic mass of carbon 12.011 U, oxygen 16.00 U. Now molar mass of carbon dioxide, 1 carbon and 2 oxygen atoms, that is 12.011 U plus 2 into 16 U, that is 44.011 gram per mole. Number of molecules of carbon dioxide equals, the mass given is 31.6 into 1 mole carbon dioxide by 44.011 into the next conversion factor 6.022 into 10 raised to 23 molecules by 1 mole carbon dioxide. That is 4.32 into 10 raised to 23 molecules. So 31.6 gram carbon dioxide contains 4.32 into 10 raised to 23 carbon dioxide molecules. We can do the calculation in another way. First we calculate the number of moles of carbon dioxide, that is mass divided by molar mass, that is 31.6 divided by molar mass of carbon dioxide, that is 31.6 by 44.011 gram per mole equals 0.718 mole. Now number of molecules of carbon dioxide equals 0.718 mole into Avogadro constant 6.022 into 10 raised to 23 molecules per mole, that is 4.32 into 10 raised to 23 molecules. Let's consider the Avogadro's law once again. That is, equal volumes of all gases at the same temperature and pressure should contain equal number of molecules, or equal number of molecules of different gases at the same temperature and pressure occupy equal volumes. Taking the second definition, equal numbers of molecules of different gases at the same temperature and pressure occupy equal volumes. Here the number of molecules, we take it as Avogadro number 6.02 in 10 raised to 23, and that is 1 mole. Now the temperature and pressure we take as 0 degrees Celsius or 273.15 Kelvin and a 10 raised to 5 Pascal, that is pressure, that is 1 bar. And this temperature and pressure is called STP, standard temperature and pressure. Now the volume of gas is taken as the molar volume, that is volume of 1 mole of gas. Thus, two samples of gas at the same temperature and pressure, the relation between volumes and numbers of moles can be represented as V1 by N1 is equal to V2 by N2, that is at constant temperature and pressure. In general, we can say volume is proportional to number of moles. The Avogadro law can be restated as, at constant temperature and pressure, the volume V occupied by a gas sample is directly proportional to the number of moles N of the gas. The volume occupied by 1 mole of a gas at a standard temperature and pressure, STP, is denoted to as the standard molar volume. It is nearly constant for all gases. The standard volume of an ideal gas is taken to be 22.711 liters per mole at STP. An ideal gas is one which obeys the gas laws. But real gases show deviation from this value. which shows that real gases do not behave ideally. For example, for hydrogen, the volume is 22.724 liter per mole. For helium, it is 22.722 liter per mole. For nitrogen, 22.701 liter per mole. Oxygen, 22.689 liter per mole. Earlier, STP was taken as 1 atmosphere pressure and 273.15 Kelvin. Then molar volume was taken as 22.414 liter per mole at STP for an ideal gas. Suppose that we have three gases A, B and C. The number of molecules for gas A be 6.022 in 10 raised to 23, that is 1 mole, and suppose that it is at a temperature 273.15 Kelvin or 0 degrees Celsius and a pressure of 1 bar, that is STP. Then the gas will occupy a volume of 22.71 liter. Let gas B contain 6.022 into 10 raised to 23, that is same as A, that is 1 mole, and let it be at 273.15 Kelvin or 0 degrees Celsius and 1 bar pressure, that is the gas at 1 mole of gas at STP. Now this gas also will occupy a volume of 22.71 liter. Coming to gas C, let it also contain 6.02 in 10 raised to 23 molecules, that is 1 mole, and let the gas be at 273.15 Kelvin and 1 bar pressure, that is at STP. The gas will occupy a volume of 22.71 liter. The unit for pressure bar is approximately equal to atmosphere, abbreviated as ATM. 1 atmosphere equals 1.01325 bar. The SI unit is Pascal. That is 1 bar equals 10 raised to 5 Pascal. And 1 atmosphere equals 1.01325 into 10 raised to 5 Pascal. 1 Pascal is equal to 1 Newton per meter square. Let us work out some multiple choice questions and numerical questions based on the topics we have studied under part 3, that is laws of chemical combination, atomic mass, molecular mass, mole concept, etc. 3 samples of magnesium oxide were analyzed to determine the mass ratios oxygen by magnesium, which gave the following result: 1.6 gram oxygen upon 2.43 gram magnesium, 0.658 gram oxygen upon 1 gram magnesium, 2.29 gram oxygen upon 3.48 gram magnesium. The law or laws of chemical combination that is or are explained by these data is: 1. The law of conservation of mass, 2. The law of multiple proportion, 3. The law of definite proportion, 4. The law of definite proportion and the law of conservation of mass. Let us first calculate the ratios. Sample 1, 1.6 gram oxygen by 2.43 gram magnesium equals 0.66. Sample 2, the ratio is 0.658. For sample 3, the ratio is 0.658. All the ratios are found to be the same. Hence, the law of definite proportion must be the answer. Option 3 is the correct answer. Question 2. Which of the following reaction is not correct according to the law of conservation of mass? Option 1, option 2, option 3, option 4. 4 equations are given. For option 2, the number of atoms of each kind are not the same. So 3 carbon atoms here only 1 carbon atom, 8 hydrogen atom here, only 2. That means it is not a balanced equation. So the answer is option 2. Question 3. A sample of sulfur weighs 8 gram. The number of moles of sulfur atoms and the number of sulfur atoms present in the sample respectively are given. Atomic mass of sulfur 32.1 U, Avogadro constant 6 into 10 raised to 23 per mole. Option 1, option 2, option 3, option 4. Atomic mass of sulfur is 32.1 U. Therefore, molar mass is equal to 32.1 gram per mole. The number of moles is mass by molar mass. That is 8 gram by 32.1 gram per mole, and that is 0.25 mole. The number of atoms is equal to number of moles into Avogadro constant. That is 0.25 mole into 6 into 10 raised to 23 atoms per mole. That is 1.5 into 10 raised to 23. Correcting to the required number of significant figures, 2 into 10 raised to 23 atoms. So here for Avogadro constant, the number of significant figures is 1. Therefore, answer should be in 1. Option 4 is the correct answer. 0.25 moles and 2 into 10 raised to 23 atoms. Question 4. The number of atoms present in 1 mole of an element is equal to Avogadro number. Which of the following element contains the greatest number of atoms? 4 gram helium, 46 gram sodium, 0.4 gram calcium, and 12 gram helium. First, we have to calculate the number of moles. Molar mass of helium is 4 gram per mole. So the number of moles in 4 gram, that is 4 gram divided by 4 gram per mole, and that is 1 mole. Then 46 gram molar mass of sodium is 23. Therefore 46 gram equals 46 by 23 equal 2 mole. Molar mass of calcium is 40.08 gram per mole. Therefore 0.4 gram, the number of moles will be 0.4 gram divided by 40, that is 0.01 mole. Molar mass of helium is 4 gram per mole, so 12 gram will be 12 by 4, 3 moles. So the greatest number of atoms will be in 3 mole, that is 12 gram. Which of the following statements indicates that law of multiple proportion is being followed? 1. Sample of carbon dioxide taken from any source will always have carbon and oxygen in the ratio 1:2. Carbon atoms form two oxides, namely carbon dioxide and carbon monoxide, where mass of oxygen which combine with the fixed mass of carbon are in the simple ratio 2:1. When magnesium burns in oxygen, the amount of magnesium taken for the reaction is equal to the amount of magnesium in magnesium oxide formed. At constant temperature and pressure, 200 ml of hydrogen will combine with 100 ml oxygen to produce 200 ml of water vapor. The first one is not the law of multiple proportion, and that is law of definite proportion. Now come to the second question. Carbon forms two oxides. Therefore, option 2 represents the law of multiple proportion. Question 6. Which of the following statements is related to the law of conservation of mass? Option 1, option 2, option 3, option 4. 12 gram carbon combined with 16 gram oxygen giving 28 gram carbon monoxide. Therefore, the total mass before the reaction, that is 12 plus 16, 28, and amount of carbon monoxide formed also is 28. That is, the total mass before and after reaction is the same. So option 1 represents law of conservation of mass. In option 2, sample of nitrogen gas at constant pressure when heated, its volume is increased, and that is not related to any law. When 5 gram iron is heated in vacuum, its mass remains the same. In this case, only temperature increases. The mass of a piece of magnesium is the same before and after heating in air. this is not the same. Mass will be different. Magnesium will be converted to magnesium oxide. Question 7. When two samples of lead oxide were separately reduced to metallic lead by heating in a current of hydrogen, the mass of metallic lead obtained from one oxide was found to be half of that obtained from the other oxide. The data explains option 1 law of conservation of mass, option 2 law of definite proportion, option 3 law of multiple proportions, option 4 no specific law of chemical combination. When two samples of lead oxide are separately reduced to metallic lead by heating in a current of hydrogen, the mass of the metal combining with the fixed mass of hydrogen are different in two oxides. So the law of multiple proportion is represented by the data. Question 8. Chromium has 4 isotopes. The isotopic masses and relative abundances are given below. The atomic mass of chromium will be very near to option 1 52U, option 2 50U, option 3 53U, option 4 54U. Since we cannot use calculator in the examination hall, we can make a guess. So if we take the average value related to the abundance, 52 chromium is having the maximum or the highest abundance. So the atomic mass will be very near to 51.9405. That is, it should be 52. Let us calculate it. So this is the way in which the atomic mass of chromium is calculated. That is, exact value will be 51.996U. So our guess is correct. That is 52U. Question 9. The following data are obtained when gaseous nitrogen and gaseous oxygen react together to form different compounds. 4 compounds are formed. Mass of nitrogen, mass of oxygen. The data explains 1 law of conservation of mass, law of definite proportion, Avogadro's law, and 4 law of multiple proportion. So in compound 1, 14 gram nitrogen combines with 16 gram oxygen. In compound 2, 14 gram nitrogen combines with 32 gram oxygen. In compound 3, 14 gram nitrogen combines with 0.8 gram oxygen. That is, keeping the mass of nitrogen same, 28 gram combines with 16. Therefore, 14 grams combines with 8 gram. Here 28 gram combines with 80. So therefore, 14 gram nitrogen will combine with 40 gram oxygen. Now the mass of nitrogen is constant. Different masses of oxygen combining with a fixed mass of nitrogen are 16, 32, 8 and 40. Now there exists a simple ratio between these masses, that is 2 is to 4 is to 1 is to 5. Therefore the data shows the law of multiple proportion. Question 10. Which of the following pairs have the same number of atoms? Option 1, 16 gram of oxygen and 4 gram of hydrogen. Option 2, option 3, option 4. In this case, we have to calculate the number of atoms or molecules in each pair. Let us take first option. 16 gram oxygen means number of moles 16 gram by 32 gram per mole, 0.5 mole of oxygen. Therefore, number of molecules is 0.5 into Avogadro number of molecules. And one molecule of oxygen contains 2 atoms. Therefore, multiplying by this quantity by 2 gives the number of oxygen atoms. 4 gram hydrogen gas, 4 gram by 2 gram per mole, that is 2 moles of hydrogen molecules 2 into Avogadro number of molecules, and one hydrogen contains 2 atoms. Therefore, multiplying this quantity by 2, that is 4 into Na atoms. Therefore, this pair will not contain equal number of atoms. Coming to second option, 14 gram of nitrogen, that is 14 by 28, 0.5 moles of nitrogen molecules, 0.5 into Avogadro number, this much number of molecules of nitrogen. One nitrogen contains 2 atoms, therefore multiplying by 2, the number of atoms is 1 into Na atoms. 44 gram carbon dioxide, 44 gram by 44 gram per mole, 1 mole of carbon dioxide, that is 1 into Na molecules, and one molecule contains 3 atoms, so multiplying by 3 into Avogadro number of atoms. So in this pair also the number of atoms are not the same. Option 3, 28 gram of nitrogen, that is 1 mole of nitrogen molecule, 1 into Avogadro number of molecules. One nitrogen molecule contains 2 atoms, so 1 into 2, 2 into Na atoms. Now 32 gram of oxygen molecule, 32 by 32 gram per mole, that is 1 mole of oxygen, and that is 1 mole of, or 1 into Avogadro number of molecules of oxygen. One oxygen contains 2 atoms, so 2 into Na atoms. Fourth one, 24 gram of carbon, 24 by 12 gram per mole, that is 2 moles, 2 into Na atoms. 23 gram of sodium, that is 23 by 23 gram per mole, 1 mole of sodium atom. In option 3, the number of atoms both are the same. In all other cases, the number of atoms are different. So option 3 is the correct option. Question 11. One of the statements of Dalton's atomic theory is given below. Compounds are formed when atoms of different elements combine in a fixed ratio. Which of the following laws is not related to this statement? Law of conservation of mass, law of definite proportion, law of multiple proportion, Avogadro law. And this statement is not related to the Avogadro law. This statement is related to all these three: law of conservation of mass, law of definite proportion, as well as law of multiple proportions. Question number 12. Dalton's atomic theory could not explain which of the following: the law of conservation of mass, law of constant proportion, law of multiple proportion, and the law of gaseous volumes. Dalton's atomic theory could not explain law of gaseous volumes. Dalton did not consider the concept of molecules. Question 13. The highest number of helium atom is in 1. 2.71098 liter of helium at STP, 4 mole of helium, 4 atomic mass unit of helium, 4 gram of helium. So we have to calculate numerically the number of atoms in each case. Option 1. We know 22.71 liter of helium at STP contains 1 mole. That is 6.022 into 10 raised to 23 atoms of helium. Therefore, 2.271098 liter of helium at STP contains, we can take it approximately as 2.271 liter. That is 2.271 liter into 1 mole by 22.71 liter into 6.022 into 10 raised to 23 atom per mole. And this comes out to be 6.02 into 10 raised to 22 atoms. Second option, 4 mole helium contains 4 mole into 6.022 into 10 raised to 23 atom per mole. that is 2.4 into 10 raised to 24 atoms. Option 3, 4U means atomic mass unit. 4U is the atomic mass of helium, which means one atom of helium is 4 times heavier than 1 by 12 the mass of a carbon 12 atom. We can consider it as representing one atom of helium. Fourth option, molar mass of helium is 4.003 gram per mole. Therefore, 4 gram helium is 1 mole of helium, and that equals 6.022 into 10 raised to 23 atoms. So among these, the highest number of atoms is option 2, that is 4 mole of helium, 2.4 into 10 raised to 24 atoms. So option 2 is the correct answer. Question 14. 1 mole of a gas occupies 27 liter and its density is 1.41 gram per liter at some temperature and pressure. The density of the gas at STP will be option 1, option 2, option 3 and option 4. And since it is a numerical question, we have to calculate the value. Since molar volume and density are given, we can calculate molar mass. That is 1.41 gram per liter density into molar volume 27.0 liter per mole, that is 38.1 gram per mole. At STP 1 mole, here it is 38.1 gram, would occupy 22.7 liter. Hence the density at STP will be mass by volume 38.1 by 22.7, that is 1.68 gram per liter. So the answer is option 1. Question 15. The number of molecules in 500 ml carbon tetrachloride whose density is 1.59 for gram per ml is, molar mass is given, molar mass of CCl4 is 153.81 gram per mole. Option 1, option 2, option 3 and option 4. Let us make the calculation. Mass of CCl4 equals volume into density. Volume is 500 ml, density is this one. So that is 797, and since the number of significant figures is 1 here, we reduce it to one significant figure, that is 8 into 10 raised to 2, that is 800 gram. Molar mass of CCl4 is given 153.81 gram per mole. Therefore, the number of moles of CCl4 is 800 by 153.81 gram per mole, that is 5 mole, corrected to the required number of significant figures. Hence, the number of CCl4 molecules is 5 into Avogadro constant, that is 30.02 into 10 raised to 23, 3 into 10 raised to 24 molecules. So option 2 is the correct answer. Which of the following weighs most? 1 gram atom of nitrogen, 1 mole of water, 1 mole of sodium, 1 molecule of magnesium oxide. We have to find the masses of each. Atomic mass of nitrogen 14U, therefore 1 gram atom of nitrogen will be 14 gram per mole. Then 1 mole of water 18 gram per mole, 1 mole of sodium, atomic mass 23, that is 23 gram per mole. Now it is 1 molecule of magnesium oxide, it is 40.3U, and we know 1 U or 1 AMU is equal to 1.66056 into 10 raised to minus 24 gram. Therefore, the mass of 1 molecule of magnesium oxide will be in the order of 10 raised to minus 23 gram. Therefore, 1 mole of sodium weighs most. So the answer will be option 3. Question 17. Which of the following contains the same number of carbon atoms as are in 6 gram of carbon 12? 6 gram of ethane, 8 gram of methane, 21 gram of propane, and fourth option 28 gram of carbon monoxide. First, we have to find out the number of carbon atoms present in 6 gram of carbon 12. Number of carbon atoms in 6 gram of carbon 12 equals 6 gram divided by 12 gram per mole into Avogadro constant, that is 0.5 Na. Molar mass of methane is 30 gram per mole. Therefore, the number of moles of methane is 6 gram divided by 30 gram per mole, that is 0.2 mole. Number of carbon atoms. One methane molecule contains 2 carbon atoms. So therefore 0.2 mole into 2 into Avogadro constant, and that is equal to 0.4 Na. The second option, 8 gram of methane. Molar mass of methane is 16 gram per mole. Therefore the number of moles of methane in 8 gram is 8 gram divided by 16 gram per mole, that is equal to 0.5 mole. One molecule of methane contains 1 carbon atom. Therefore, the number of carbon atoms in 0.5 moles is 0.5 mole into 1 into Avogadro constant, that is equal to 0.5 Na. Therefore, 8 gram of methane contains the same number of carbon atoms as in 6 gram of carbon 12. Therefore, the answer should be option 2. 21 gram of propane. Molar mass of propane is 44 gram. Therefore, the number of moles is equal to 21 by 44, that is 0.48 mole. Number of carbon atoms is equal to 0.48 mole into 3. Propane contains 3 carbon atoms in the Avogadro constant, and that is equal to 1.44 Na. 28 gram of carbon monoxide. Molar mass of carbon monoxide is 28. Therefore, number of mole is 0.1 mole. Therefore, the number of carbon atoms, carbon monoxide contains only 1 carbon atom, so it is 1 Na. Question 18. The following data are obtained for compounds of nitrogen and hydrogen. Compound mass of nitrogen, mass of hydrogen. Compounds A, B and C. Masses given. If the formula of compound B is N2H2, what are the formulas of A and C? Option 1, A N2H6, C N2H4. Option 2, A N2H4, C NS2. Option 3, A N2H4, C NS3. And option 4, A NS3, C N2H4. Since nitrogen and hydrogen forms different compounds, this data is consistent with the law of multiple proportion. So we have to find the mass of hydrogen combining with a fixed mass of nitrogen. In compound A, 0.5 gram nitrogen combines with 0.18 gram hydrogen. So 1 gram nitrogen combines with 0.108 into 2, that is 0.216 gram hydrogen. In compound B, 1 gram combines with 0.072 gram hydrogen. In compound C, 1 gram 0.75 gram combines with 0.108 gram. Therefore, 1 gram nitrogen combines with 0.108 divided by 0.750, that is 0.144 gram. Now, the ratio of the different masses of hydrogen combining with a fixed mass of nitrogen is 0.216 is to 0.072 is to 0.144. So we divide with the smallest number and the ratio comes to be 3 is to 1 is to 2. So we can assume that in A, 1 nitrogen combines with 3 hydrogen, and in B, 1 nitrogen combines with 1 hydrogen, and in C, 1 nitrogen combines with 2 hydrogen. But the formula of B is N2H2, that is 2 nitrogen combines with 2 hydrogen. Therefore, A may be N2H6 and C may be N2H4. Since N2H6 is highly unstable, A will be NS3. So, option 4 is more correct. A is NS3 ammonia, B N2H2 diazine, C N2H4 hydrazine. Question 19. Arrange the following in the order of increasing mass. Atomic mass of oxygen 16U, that of copper 63U, and nitrogen 14U. 1 mole of oxygen, 1 atom of nitrogen, 1 into 10 raised to minus 10 mole of oxygen molecules, 1 into 10 raised to minus 10 gram of copper. Option 1, option 2, option 3, option 4. First, 1 molecule of oxygen. Molar mass of oxygen molecule is 2 into 16. 2 oxygen atoms are there. So it is 32 gram per mole. So mass of 1 molecule of oxygen is 32 gram per mole divided by Avogadro constant, that is 5.3 into 10 raised to minus 23 gram. Then second one, 1 atom of nitrogen. Molar mass of nitrogen is 14 gram per mole. Mass of 1 atom will be 14 gram per mole divided by Avogadro constant, that is 2.3 into 10 raised to minus 23 gram. Third one, 1 into 10 raised to minus 10 mole of oxygen molecules. Molar mass of oxygen molecule is 32 gram per mole. So mass of 10 raised to minus 10 mole is equal to 10 raised to minus 10 mole into 32 gram per mole. That is 3.2 into 10 raised to minus 9 gram. Then fourth one, 1 into 10 raised to minus 10 gram of copper. Mass of copper is 10 raised to minus 10 gram. Therefore, the order could be taken as option 1. Question 20, an assertion reason question. Assertion, one atomic mass unit is defined as 1/12 of the mass of one carbon-12 atom. Reason, carbon-12 isotope is the most abundant isotope of carbon and has been chosen as standard. Option 1, option 2, option 3 and option 4. On initial reading, you may choose option 1 as the answer, but it is not the correct answer. That is, the reason does not explain clearly the assertion. So it can be explained in the following way. When we study atomic structure, we will see that carbon-12 nucleus contains exactly 6 protons and 6 neutrons. By defining AMU as 1/12 of carbon-12 makes the mass of a proton and neutron very near to 1 AMU. This approach therefore ensures that the atomic masses of most other elements are expressed as numbers close to their mass number, simplifying chemical and physical calculations. The reason for selecting carbon-12 is the following. Carbon-12 was chosen because it is isotopically pure, stable, easy to handle, mid-mass, that is reducing relative error, and it resolves historical inconsistencies between physics and chemistry atomic mass scales. Next, we will discuss some numerical questions. Question 1. The following values of isotopic mass, that is given in brackets, and abundances are obtained for magnesium with the mass spectrometer. Compute the atomic mass of magnesium. Magnesium, percentage abundance 78.7. The corresponding atomic mass is this one. Percentage abundance 10.13. Atomic mass this one. And 11.1 atomic mass this one. Atomic mass of magnesium is the weighted average of the masses of these 3 isotopes. That is 78.7%. If we take 100 gram, it will contain 78.7 gram of this isotope. So it is 78.70 by 100 into 23.98504. That is the atomic mass. Plus 10.13, that is the percentage abundance by 100 into 24.98584. Plus the third one, 11.17 by 100 into 25.98259. And this is actually the fractional abundance. And finally we get the values as 24.3095375 U. The final value could be taken as 24.3095473 U. Question 2. If 10 volumes of dihydrogen gas reacts with 5 volumes of dioxin gas, how many volumes of water vapor would be produced? From Gay-Lussac's law, we know gases react in simple whole number ratios of their volumes. The reaction between hydrogen and oxygen could be written like this. 2 moles of hydrogen react with 1 mole of oxygen, giving 2 moles of water vapor. That means 2 volumes of hydrogen plus 1 volume of oxygen gives 2 volumes of water vapor. So the ratio is 2:1:1. Therefore, when 10 volumes of dihydrogen react with 5 volumes of dioxygen, we get 10 volumes of water vapor. Question 3. When 3.06 gram hydrogen was allowed to react with an excess of oxygen, 27.35 gram water was obtained. In a second experiment, a sample of water was decomposed by electrolysis, resulting in 1.45 gram hydrogen and 11.51 gram oxygen. Which law of chemical combination is interpreted by this data? Now, the mass of oxygen used in the first experiment is 27.35 minus 3.06. Therefore, 24.29 gram. So, mass of water obtained is 27.35. So, subtracting 3.06 will give the mass of oxygen. Ratio of mass of oxygen and hydrogen is 24.29 gram by 3.06, that is 7.94. Now the mass of oxygen obtained in the second experiment, that is electrolysis, that is 11.51 gram, and the mass of hydrogen obtained is 1.45 gram. Ratio of mass of oxygen and hydrogen is 7.94, same as the first one. In both the experiments, the oxygen is to hydrogen ratio are the same. Hence, the data demonstrate the law of definite proportion. Question 4. Phosphorus forms 2 compounds with chlorine. In the first compound, 1 gram of phosphorus is combined with 3.433 gram chlorine, and in the second, 2.5 gram phosphorus is combined with 14.308 gram chlorine. Show that this data is consistent with the law of multiple proportion. The law of multiple proportion is if 2 elements can combine to form more than one compound, the masses of one of the element that combine with a fixed mass of the other are in the ratio of simple whole numbers. Take compound 1. In that, 1 gram phosphorus combined with 3.433 gram chlorine. But in the second one, 2.5 gram phosphorus combines with 11.308 gram chlorine. Therefore, 1 gram phosphorus will combine with 14.308 by 2.5 into 1, that is 5.732 gram. So in these two compounds, the different masses of chlorine combines with a fixed mass of phosphorus is 3.433 and 5.732. So the ratio of different mass of chlorine combined with 1 gram of phosphorus could be taken as 5.732 by 3.433, that is 1.670 by 1, or the ratio is 1:1.670. Now we make it a whole number, multiply by 3, we get 3:5, and 3:5 is a simple ratio. Hence the law of multiple proportion. Question 5. Hydrogen gas is prepared in the laboratory by reacting dilute HCl with granulated zinc. The following reaction take place. Zinc plus 2 HCl giving zinc chloride plus hydrogen gas. Calculate the volume of hydrogen gas liberated at STP when 32.65 gram of zinc reacts with HCl. Atomic mass of zinc is 65.3 U. Atomic mass of zinc is given, that is 65.3 U. Therefore, molar mass of zinc is 65.3 gram per mole. From the equation, 1 mole of zinc reacts with the 2 moles of HCl, giving 1 mole of hydrogen gas. That is 63.5 gram zinc produces 2.018 gram hydrogen gas. Molar mass of hydrogen is 2.018. Hence 32.65 gram of zinc will produce 2.018 divided by 6.65.3 into 32.65, that is 1.01 gram. Number of moles of hydrogen produced equals this divided by this one, that is 0.5 mole. 1 mole of a gas occupies 22.71 liter at STP. Therefore, 0.5 mole of hydrogen will occupy a volume of 22.71 liter divided by 1 mole into 0.5 mole, that is 11.36 liter. Question 6. Calculate the number of oxygen atoms present in 7.57 liter of oxygen gas at STP. We know 22.71 liter of a gas at STP contain 1 mole of the gas. Therefore, the number of moles of dioxin present in 72.57 liter at STP equal 1 mole divided by 22.71 liter into 7.57 liter. That equals 0.333 mole. 1 mole of dioxin contains 2 into 6.02 into 10 raised to 23 oxygen atoms. Therefore, 0.33 mole dioxygen will contain 0.333 mole into 2 into 6.02 into 10 raised to 23 atoms per mole, or that equals 4.01 into 10 raised to 23 atoms. Thank you for watching my video. For the next video, either go to the links given in the description part or click here.